Hannah Christensen from the University of Oxford is the 2014 Keith Runcorn Thesis Prize winner, and firstly I'm going to give her a certificate, so congratulations.
Thank you.
And she's going to talk about, can randomness reduce uncertainty, the use of stochastic physics in weather and climate prediction.
Right, so I think it needs to go back a very long way, I'm afraid. Okay, great. Thank you very much. Thank you for inviting me here today to give this talk. So I'm going to talk to you about some of my thesis work. And the question I want to address in the talk is, can randomness reduce uncertainty? And we're going to be looking at the use of stochastic physics then in weather and climate prediction. Okay, so first of all, I want to ask the question, can we trust this forecast? So I pulled this off the internet this morning. So this is showing us the deterministic, or the best guess forecast, I suppose, for the weather for the coming week. So this is the weather forecaster who made this thinks that this is then the most likely weather that we're going to see in London over the weekend and then for the coming week. And overwhelmingly, the public would say, no, we can't trust this forecast. So this... Great, yeah, so this cartoon was written in response to the news that the Met Office has just been given a lot of money for a new supercomputer. And the caption then reads, with our new super-fast computers, we can get the forecast wrong twice as fast as we used to. But what I think this implicitly says is that the public always takes the weather forecast with a pinch of salt. So they expect the forecast to be wrong to some extent. But this is interesting then, because if we only give the public a best guess forecast, they then infer some uncertainty information on top of this forecast. So unfortunately for the weather forecaster, the cases that they tend to remember are the cases when we got the forecast very wrong. So perhaps the best example of this then is the infamous forecast made by Michael Fish on the evening of the Great Storm of 1987. So the forecast he gave was, earlier today, a woman rang the BBC and said that she was worried a hurricane was on the way. Well, if you're watching, don't worry, there isn't. People woke up the following morning to scenes like this. It was the strongest windstorm in the south of the UK for many years. But this is the forecast that Michael Fish would have had access to. So this is the best guess forecast for that night, a fairly run-of-the-mill low-pressure system, nothing out of the ordinary. This is what actually happened then, a very deep low-pressure system, very close isobars leading to very strong winds. So what we do these days is that instead we can make a probabilistic forecast. So again, what I'm showing here is the observed pressure field and the best guess. But now what we're also showing is 50 equally likely possible evolutions of the atmosphere for that day. So what we can see is that some of them are indeed showing what the best guess forecast said, no storm, but some of them are now revealing this likelihood for having a very strong storm. So I suppose what this is trying to motivate is how important it is to then include a representation of uncertainty in our forecast and how much extra information we can get by doing this. A property of our forecast that we particularly want then is that this forecast should be reliable. So what we do is we generate a set of equally likely forecasts where the range in these forecasts indicates the uncertainty. And in order to be reliable, this PDF should really be statistically consistent. So we want the PDF to really indicate the uncertainty in the forecast. So you can frame this in terms of this question here. So say if your forecast predicts that it's going to rain tomorrow with a 20% likelihood, if we collect all the days we made this forecast together and look at what happened, does it rain 20% of the time? Now rain is a binary event, but we can frame this in terms of a continuous variable here. So what we're really wanting to know is, does our observation follow this probability distribution? We can summarize this diagnostic to some extent by comparing the standard deviation of our forecast PDF with the root mean square error in the ensemble mean, where we calculate these statistics over many, many forecast cases. Okay, so in order to achieve a reliable forecast, we have to represent all sources of uncertainty in our forecast. So the first uncertainty we need to represent is initial condition uncertainty. So this arises from the fact that we only have limited satellite and weather balloon data with which to estimate the current state of the atmosphere and to initialize our model. And very small errors in estimates of the starting conditions can pan out into very large differences in the forecast. So we can represent this very simply by perturbing the starting conditions of our ensemble members within our estimate of uncertainty. And for the case of the Great Storm of '87, this is actually enough to really show the unpredictability of the atmosphere. And it arises because the atmosphere is a chaotic system. So in some cases, so this is the Lorenz 63 chaotic attractor here. So in some cases, if we generate a little ensemble of forecasts, we find that after a very short time, the different trajectories rapidly diverge. And so this is what happened with the Great Storm then. The atmosphere was kind of teetering on a knife edge, I suppose. And our best guess was that it would teeter one way and be a very calm evening, but actually it went the other way. But I suppose interestingly, other times when we generate one of these perturbed ensembles, we find that they stick very close together out to quite long lead times. So there are occasions when we have a lot of predictability in the atmosphere. So the second source of uncertainty which we must represent is model uncertainty. And so this arises very simply because we're using a computer model to make a forecast, and a computer model is not the same as the real atmosphere. We build one of these models by taking our equations of motion which describe the atmosphere, so the Navier-Stokes equations, the continuity equation, thermodynamic equations, and we discretize them onto some grid, which is what this is showing here. And so in the case of a weather forecasting model, a grid box is about 10 or 15 kilometers in size. So this is a fairly coarse grid. Anything that scales smaller of this then has to be approximated. So this is things like clouds and radiation, the effects of orography. And we approximate these using parametrization schemes. And so, this includes many simplifications into the model. But errors introduced in this way can then also go rapidly in time because it's a chaotic system. So we have to represent this source of uncertainty. And so while within the community we're fairly happy with the best way to represent initial condition uncertainty, there's a lot of disagreement as to the best way to represent model uncertainty. So this was then really the topic of my thesis and what the rest of the talk is going to be on. In particular, I'm going to be comparing two proposed methods for representing model uncertainty. The first are called stochastic parameterization schemes, and the second is called a perturbed parameter scheme. Okay, I'm going to say a bit more about those schemes in a few minutes, but in the context of this very simple system. So I started off by testing these representations of uncertainty in this Lorenz 96 system, which you can think of as a toy model of the atmosphere. So it consists of this set of coupled equations here, in two different scales of variables. So the x variables are large scale and low frequency, arranged in a ring as shown. So you can think of these as representing then large scale atmospheric phenomena, so for example a big low pressure system over the UK. Each x variable is coupled to many small scale high frequency y variables. So you can think of these as representing, say, individual convective clouds. You can see that the small scale y variables are driven by what their parent x variable is doing, but importantly that they also in turn affect what the x variable does. So we can set up a very idealized experiment in this model. We can run the full set of equations and define this to be our real atmosphere, what we're observing out the window. And then we can play a game where we say we want to make a weather forecast of this system, but we only have limited computer resources. So sadly, we're going to have to truncate our model. Our y variables are unresolved. This is very similar then to how we make a real weather forecast when a convective cloud is unresolved. But we have to represent the impact of the y variables on the x variables. So we build these parametrization schemes that I've just mentioned, and then we can run a forecast in this reduced system. But because we have this full true model with the two scales of variables, we can plot exactly what this term should look like as a function of x. And so that's what I'm showing here. So on the y-axis we have this subgrid tendency u as a function of x. So in a kind of best guess weather forecasting model, what we do is we generate a parameterization scheme which represents the most likely impact of this subgrid scale on the resolved scale. So that's given then by this deterministic black line parameterization scheme, which here is just a cubic polynomial fitted to the data. But we can now really see what this model uncertainty is. So there's a huge amount of scatter in reality about this best guess parameterization, and that's what we then try and represent using these two different schemes. So firstly, we can build a perturbed parameter scheme. So the idea is that within any parameterization scheme, there are many physical parameters which are poorly determined. We can take their values and change them between ensemble members to then explore the uncertainty that arises due to this poor constraint. So what we've done here is we've taken the parameters in our deterministic model, which are the cubic fit parameters, and we've perturbed them, we've changed them between ensemble members to then generate what is in effect an ensemble of forecast models. And we can estimate the degree to which we should perturb them by fitting this cubic polynomial to subsets of the data. So the second approach then is a stochastic parameterization scheme. So in this approach, we use random numbers in our equations of motion to try and represent the error between our forecast model and the true atmosphere. So in other words, in our deterministic parameterization, what we're doing is we're representing the most likely affect u as a function of x. But a stochastic scheme recognizes that actually all x does is it constrains what the PDF of u could be, and it doesn't determine its exact value. So we can use a stochastic scheme where we draw values from this PDF in some way to investigate then what one potential realization of the atmosphere could have on the large scale. So I investigated several different schemes, but the one which I'm just going to present here is the simplest, the additive noise case, where we take the deterministic parameterization as our starting point, and then we add a random number on the end to represent this error, this difference between the grey cloud and the black line. And we can measure the statistics of this error from our true model. So in particular, we can measure the standard deviation and the temporal correlation. So for both of these different representations of uncertainty, I'm going to run a 40-member ensemble forecast. But importantly, I'm initializing all ensemble members from perfect initial conditions. So I've removed initial condition uncertainty, and we're just evaluating what the best representation of model uncertainty is. Okay, so here's some results looking then at the reliability of the forecasts. So I said before that you can compare the root mean square error in the ensemble mean with the root mean square spread on the ensemble. And if these two equal each other on average, then you've got a reliable forecast. So firstly, we can look at our deterministic, our best guess forecast. By construction, there's no spread in the forecast. So this doesn't give us any indication of how certain we can be in our forecast. So it's completely unreliable. We can then move to one of the stochastic parameterizations. Here, this is the additive case, but where I'm using white noise. So each draw from our random number generator is independent of the previous numbers. We can see we get an improvement in reliability, but we're still under-dispersive. So the spread is systematically smaller than the error. Our forecast is overconfident. Also, the gradient is very steep, especially at small spreads. So this means we're not really distinguishing very well between these more certain and less certain cases. The perturbed parameter ensemble that I generated looks very similar to the white additive scheme. But on the other hand, the red noise stochastic parameterization performs very well and gives you a very reliable ensemble. So coming back to the question at the beginning of the talk, I'd say that this motivates the fact that randomness can then in some cases reduce the uncertainty in the forecast. If you use a stochastic parameterization scheme and it indicates that your spread is very small, then you as the user of the forecast can be very certain in that result. So I then moved on to ask exactly the same question, but in a full operational weather prediction model. So this is the model I'm using is the IFS. It's the model used by the European Centre for Medium Range Weather Forecasting in Reading. And this is a schematic of the different physics parameterization schemes in that model. So there's clouds and convection, radiation schemes, subgrid scale orography, turbulence. And these are then all the things that are approximated in the model that are not explicitly calculated. So in particular, I'm going to look at the best way to represent uncertainty in the convection scheme. And this is because convection is thought to be the physical parameterization scheme which the models are most sensitive to, which is most uncertain. Within this scheme, then, I'm going to compare a new perturbed parameter scheme that I've developed with various stochastic parameterization approaches to see which is the best representation of uncertainty. Now, the IFS operationally uses two stochastic schemes. So the first is called the spectral backscatter scheme, which I won't say any more on, but the second is called the stochastically perturbed parameterization tendency scheme, SPPT. So SPPT is designed to represent the uncertainty in these parameterization schemes, which is then exactly akin to what we were trying to do in the Lorenz system. So we can write the model equations very simply in this form. So the total tendency, a change in a variable over a time step, in the model is given as a sum of the dynamics tendency, so then this is the change due to advection, and the tendency from the physics schemes. And so we've got the physics schemes here, radiation, clouds, convection. So in SPPT, what we do is we take this physics tendency and we multiply it by a random number. This term then has mean of 1 and a standard deviation of 1/2. So this is an enormous kick to the model. The random number is spatially smoothly correlated and also correlated in time. But this scheme then essentially works out as the operational representation of uncertainty in convection, because the convection tendency is one of the ones that's perturbed here. So the first thing I've done is do a very simple generalization to this scheme, where we've pulled the random number inside the summation term. But what this means we can do is perturb the different schemes separately. In particular, we can turn off the perturbation for the convection scheme and try out our new perturbed parameter scheme. But secondly, we can also perturb each of these 5 physics schemes with an independent random number field. I call this independent SPPT. I suppose in standard SPPT, what we're implicitly assuming is that the errors in each of the parameterization schemes are perfectly correlated. Independent SPPT then assumes perfectly uncorrelated errors. So it's interesting to see what the other extreme is. So my perturbed parameter scheme, I started off by using a Bayesian parameter estimation approach to measure the uncertainty in 4 of the parameters in the convection scheme. So you can see the estimation approach at work here. So we set it going from the operational value of the parameter, and you see quite quickly that it drifts off onto this new optimal value, but that there's still a lot of uncertainty in the parameter. So what we do is we take the joint distribution of uncertainty in the parameters, and we draw from this distribution, and I can test both a fixed and a stochastically varying perturbed parameter scheme. What we're going to look at then is 3 different kinds of representation of uncertainty. So the first, where we don't represent uncertainty in convection, the second stochastic, and the third, these perturbed parameter schemes. But I really want to stress that for all of these, we're using SPPT to represent uncertainty in the other physics schemes. So we're assuming that that's a good representation. I checked the ensemble forecasts in regions where there's very little convection occurring, and they do indeed appear to be reliable, so I think that's a good assumption. And furthermore, we're going to just show diagnostics here for areas where there's a lot of convection, so then we assume that convective uncertainty will really dominate here. Okay, so here what I'm showing is this root mean square spread error reliability diagnostic as a function of lead time in the forecast. So here now the dashed lines are the spread of the ensemble and the solid lines are the error. So we can pick out red as the operational representation of uncertainty in the model, so just normal SPPT. And then the green and the blue are our 2 new perturbed parameter schemes. And so it's certainly true that they increase the spread towards the error a little compared to SPPT, so they're improving the reliability, but the ensemble is still under-dispersive, so it's still overconfident, it's not reliable. However, the new independent SPPT scheme that we tested actually really remarkably improved the spread of the ensemble, so that's this magenta line. And so now it seems that this scheme is actually really very reliable in these areas where there's a lot of convection. And interestingly, it didn't really change the calibration of the ensemble much in areas where there's little convection. So why does this happen? Well, it really comes back to this schematic that I showed a few slides ago of how the parameterization schemes are set up in the IFS. And it's because it's set up so that the deep convection scheme deals with a lot of the warming due to convective clouds. But then at the top of the convective plume, you have this detrainment of moist air into the cloud anvil, which is then picked up by the cloud scheme. And the cloud scheme then deals with the evaporative cooling and the radiative cooling from that anvil. So if you look at the sum of the tendencies in regions where there's a lot of convection, the sum is fairly small. So in normal SPPT, we perturb this small tendency. Because it's a multiplicative scheme, this is implicitly representing the uncertainty as being small. But if we apply a different pattern to each tendency, the large convection tendency then has a large uncertainty associated with it in its independent SPPT scheme. So just to briefly sum that up, it seems that the operational stochastic representation of uncertainty is underdispersive in the IFS. Perturbed parameter schemes improve somewhat, but really this new independent SPPT scheme is the best. So we can, it's possible to develop a stochastic parameterization scheme which really does make reliable forecasts. So in my last 2 minutes, I'm just going to say a few words about climate prediction. So hopefully I've motivated why stochastic parameterization is useful in weather forecasting, but why would it be useful in the climate? Well, this quote I've taken from a very old paper from Hasselmann, where he states, he's an oceanographer, he states that slow changes of the climate are explained as the integral response to continuous random excitation by short period weather disturbances. So here these slow changes of the climate, and this could be changes on the order of decades, or it could be glacial interglacial cycles. But really we can understand this impact of the kind of variability of the weather on the climate in terms of thinking about the climate as a kind of double potential well attractor. So if in our climate model we just don't have enough weather variability, we're really only able to explore one of these two modes of our system. If we include a stochastic parameterization scheme, we improve the variability of our weather. We can start to explore this rarer regime. We see a shift in the mean and an improvement in the variability. And we do indeed see this in the Lorenz 96 model, which I was showing you earlier. So if you plot the PDF of the Lorenz system in this particular space, kind of based on the EOFs of the model, you can see that it has a major more common regime, but there's also a distinct subsidiary regime here at the top. Our deterministic model really doesn't capture that at all. It spends far too much time in the more common regime and very rarely explores up here, whereas the stochastic parameterization really enables the model to explore that rarer regime. The perturbed parameter ensemble, on the other hand, is very strange, and actually if you look at the individual members, some of them spend all their time in one regime or all their time in the other. We can also look at the impact of stochastic parameterizations then in operational climate models. So this is using this community atmospheric model, which is coupled to an ocean model, quite long historical runs. And so I'm just going to show you some results of including this SPPT scheme on the El Niño Southern Oscillation. So ENSO, it's the dominant mode of climate variability in the tropical Pacific. It's been in the news quite a lot recently because we're actually observing a very strong El Niño event at the moment. So this is what the sea surface temperature anomalies are currently looking like. It's very warm. This has a lot of impact for kind of fishing off the coast of South America. But I mean, this is a very important phenomenon, and it's important that our models can capture it well. So here I'm showing the power spectrum of a time series of average temperature in this El Niño region. And here we can see that in our control model, we have this very poor power spectrum. It's very periodic with a very dominant 3 or 4 year frequency, and the magnitude is just too large. But if we include this stochastic parameterization scheme, we really drastically improve the representation of ENSO in the model. So the grey is observations here. We've spread the power out to a wider range of frequencies, and we've actually reduced the magnitude of ENSO towards what is observed. So it seems like stochastic parameterizations are also very beneficial in climate models through their representation of the variability of these kind of short timescale weather events and unresolved subgrid processes. So in particular, they can excite the model to explore other regimes, and can also improve the representation of some of these very complicated multi-scale phenomena. So to come back to my original question then, can randomness reduce uncertainty? In weather forecasts, I feel the answer is yes. Producing reliable probabilistic forecasts can indicate to the user then how predictable the coming weather is, so whether you can be very certain about the week ahead or whether you can be less certain. In climate modelling, I think the answer is definitely a maybe. We can certainly improve the ability of a climate model to represent the real atmosphere, but this is a very young application of stochastic parametrisations. We haven't yet tested whether including these schemes in a model will actually reduce or increase our uncertainty about future climate change. So that's it. Thank you.
So if you'd like to know what the weather's going to be tomorrow, now's the time to ask. So we have time for a few questions. Quentin.
Very fascinating and lovely, and we'd love to know what the weather's like for the weekend, so if you can tell us, we'd appreciate that. I know there is a technique where you can introduce noise into a signal you're processing, and then what happens when you do the Fourier analysis, it basically gets rid of the other noise, you put it back together, and you get the crisp signal out of it. So I guess that is roughly what you're doing at this point.
So that's very relevant for the discussion about ENSO. So that's a stochastic resonance is what you're referring to. And so the idea is that if you put a white noise forcing into your system, then the system picks up the particular frequency which is characteristic of the system and then resonates with that frequency. So in that way you can magnify a signal among the noise. So that's certainly, but I suppose the thing is that would predict an enhancement of some of the variability in a system. So if you put additive noise into a very simple model of ENSO, you see it enhancing ENSO, increasing the magnitude. But I suppose what we saw, actually I can say it better in one of these figures maybe. So what we saw here is a reduction in power in ENSO when we put in the stochastic parameterization, and you can actually see this in terms of the standard deviation of the sea surface temperatures as a function of month. So it's very interesting. It doesn't seem to be kind of classic stochastic resonance, and I think in part that's because we're using a multiplicative noise term as opposed to an additive noise term, and you tend to think of stochastic resonance for additive noise. But I think it's definitely very relevant, certainly. And
the sort of follow on from that is when you obviously produce your results at the end, do you then post-process it and take out the randomness you've injected?
No, so I suppose we let the randomness is, in a weather forecasting model, the time scale of the randomness is about 6 hours and the spatial scale is about 500 kilometers. But because we're perturbing the physics tendencies themselves, then that in turn affects the flow of the model. So there's no removing of the randomness at the end. I suppose what we do, however, is, what you end up with then is a range of forecasts for the future. So if you want to work out your best guess forecast, I like to think of a stochastic parameterization scheme as somehow inverting the order of your averaging. So you can explore these possible flow situations and then average to find your best guess. Or if you use a deterministic parameterization scheme, you're kind of doing the averaging as you go along. You're putting into the model the best guess representation of a cloud within a grid box and then seeing how the model responds to that most likely cloud. Whereas in a stochastic scheme, you explore possible clouds, I suppose, and then average at the end.
I suppose the bad news for astronomers is that they don't need good seeing. The randomness there would help their results, I suppose. Thank you.
Paul.
That was a very interesting talk indeed. I wondered, but it contains extremely subtle attitudes about communicating about probability and forecasting. And I wondered if you'd given any thought as to how it is one would go about explaining this to the public at large and to the politicians, to the people who are in charge of us all, especially in relation to climate modelling, not to mention weather forecasting. Whether you've given any thought to how to get across the ideas that you've been talking about.
No, thank you. That's a really important question. I think in the realm of climate modelling, communicating uncertainty is a little bit ahead of where it is in weather forecasting in the UK, and I think that's because there are other kind of very obvious things that are uncertain about predicting the future climate, such as what carbon dioxide emission track are we going to go along. So certainly in the way that I think that's communicated fairly, or is attempted to be communicated fairly well to the policymakers, especially out of these big IPCC climate change reports. So that's very explicit in terms of what is very likely or possible or less likely in terms of impacts on the climate. For weather forecasting, I think it's a real shame that we don't actually give out more of this probabilistic information to the public. The Met Office has made some efforts in recent years to move towards this, but I think they're worried that if they just present a PDF to the public, that they'll just think they're hedging their bets in some way. So
Well, they are, but that's the nature of the equation.
Well, exactly, but I think if you can communicate to the public that some days we only know that it will rain with, say, 40% certainty, and on other days we know it's not going to rain, and other days we are much more certain, I think that would be better. There were rumours that the Met Office and the BBC fell out over the Met Office wanting to put more probabilistic information into their forecasts. But
So is that why the BBC gave up using the Met Office, or about to give up using the Met Office?
that's goes the rumours, but I think it might be also financial.
Yes. Well, perhaps we can thank our speaker again.